All right, section 2.1, brief calculus. Now do note, if you're in my course, Math 213 and Math 212 are the same thing, just one is the online version, one is the in-person version. So no matter the labeling, they're the same thing. Okay, now, as far as 2.1, we're going to start off with a little bit of prerequisite concepts. These are things that we should already have coming in with us from college algebra. And the first thing I'm going to point out is we need slope, the concept of slope. So what is slope? What is the formula for slope? Well, hopefully we remember that is slope is equal to, let me change colors, I don't want to do this in red. We should hopefully remember slope is equal to y2 minus y1 over x2 minus x1. Or what we're really saying here is we have a couple ordered pairs, whoops, x1 and y1, and then we have another ordered pair of x2 and y2. And what we're saying here is going from one point to the other, what was our change? How did we progress? What was our rise divided by our run? That might be another way of discussing it. Or the other common phrasing is change in y over change in x, right? These are all different notations, different ways of discussing it we may have seen in the past, but the big idea is it all comes down to the same thing. The question is, what is our slope? Now, what was another way of describing this? Well, we'll get back to that in a minute right here, because there might be a word that's coming through some of your heads. So we'll get back to it here with the key words. But I will say, some of you are probably itching to say, you have been yelling at the screen. My teacher always told me it's average rate of change. And I completely agree. That would be the way that we would describe slope in a word problem, right? Or in a real world application. We would have talked about what was the average rate of change? How did something change? Now, that brings us to this concept here of what would the units have been when we talk about slope? Well, when we talk about slope, maybe we would have had a graph that looks something like this, and we'd maybe have some kind of equation, some kind of function, and maybe we would put in hours and we'd get out miles, right? And so this would have described our movement, how our object was moving, measured in hours. So maybe our time, and our distance measured in miles. So what would the units of slope have been? Well, if you had two ordered pairs and we were to find the slope between those two ordered pairs, we do y2 minus y1 over x2 minus x1. And the units, though, would have been the change in y. Our y-axis was measured in miles, so it'd be change in miles, over our change in our time, which would be hours. So therefore, we would read this as miles per hour. So the key to this, whenever we were talking about slopes in real world applications, the key word was per, right? There was always a per. Maybe it was miles per hour. Maybe it was dollars per year, right? Maybe if you're running a business and how much money did you make? Well, we made this many dollars per year or per month, right? But the key word was the rate of change was a per statement. And you wouldn't need to even know much to be able to hear rate of change because you're listening for that concept of per. Maybe it was, I don't know, my favorite to go to is always turtles per cat. I don't know, but the key to this is it's a per. So you hear per. You hear that concept of per. This many of this per this. You know you're talking about a rate of change. You know you're talking about a slope, right? So now, what are the keywords that tell us to solve for slope? Well, if the question's ever asking for a per, right? A per is a tip-off. Or another tip-off is look for the word average rate of change, right? When you hear average rate of change, keyword being average, right? We're looking for from starting at this point, ending at this point, what was your rate of change? Well, that would be an average, so therefore it's slope. Okay, so be careful because sometimes students hear the word average and they think they should be, adding up the number of numbers, dividing by that, dividing by the number of numbers, and they're done. It's not that kind of average, right? It's not. We're not trying to find the average bowling score. We're trying to find the average rate of change. How quickly was something changing? All right. So be on the lookout for PERS and average. Okay, average rate of change. So let's get on to the new stuff, and we'll. Believe you me, we're going to practice doing the slope in just a minute. But let's get on to the review now, or into the new. So what are the key objectives? What are the key takeaways that at the end of this lesson you need to be able to check off and say, we need to be able to calculate average rate of change, right? So even though that's a review concept, it's still going to be something that's major in this course. So by the end, I want you to make sure you know how to do that. Then look at this. This is key. We're going to calculate the instantaneous rate of change. Please, so this, hopefully our spidey senses are tingling and we're saying, wait. We have something called average rate of change and I have something called instantaneous rate of change. So those sound very similar. So we need to figure out what the difference is between the two of them and when to do which, okay? Now notice, we are going to have many techniques actually about finding average and instantaneous rate of change. So for now, it's going to be by using 2 points that are very close together. We're going to have some other techniques to find instantaneous rate of change later using other techniques, but for now, we're just going to do it using 2 points close together. All right, so number 3 thing we need to be able to do by the end here is write an average rate of change formula using H, okay? And last but not least, be able to describe the difference in meaning between average rate of change and instantaneous rate of change. So this is going to be a major sticking point. It's going to come later, and it usually pops up. But the one key thing that students kind of struggle with is identifying if a problem has the word instantaneous rate of change, what do I do? If it has average rate of change, what do I do? And what's the difference between the meaning of the two? All right. So by the end of this lesson, hopefully we're going to be able to answer all of those things. All right. So starting off, giving you a set of data. Now, this is time measured in seconds and how far something has traveled in yards. I believe, if I remember correctly, this was based off of a car that I was measuring, but I don't remember for sure. Anyway, we're going to create a quadratic regression model. Quadratic regression model. Now, anytime in this class we ask you to create a regression, that's always using your calculator. So we're just going to start off by going into our calculator, and I'm going to reboot it because the screen doesn't want to load. And there we go. Okay, so we're going to go in and we're going to do this. Now, remember, this is a video. You can pause, you could rewind. So if you need to take a second to press buttons, pause the video. Okay, now, what we're going to do, first things first, to be able to make a regression, any kind of regression, whether it's quadratic, exponential, whatever it might be, we need to put the data in the calculator. So we are going to use the stat button, which is located just to the left of the arrow. We're going to press stat, and you're going to get a screen that looks like this. Now here on the edit screen, we want to choose option number 1, which is edit. If you already had data in your calculator, let me show you really fast. If you already had data in your calculator, you might be saying, I need to get rid of it. Well, you can do it line by line by just going to the thing you want to get rid of and pressing the delete button, DEL, which is right next to the left arrow, and that will get rid of it. But if you have a lot of data in there, then what I'm going to suggest is go all the way up to the L1 key and do not press delete, because if you do that, you will no longer have L1. What we want to do is press clear, which is the button directly below the down arrow. We're going to press clear. Now, you'll notice on the blinky screen at the bottom it says L1 equals, and it has a little blinky. If we hit enter, all of the data is cleared, but L1 remains. Okay? Now, what if, goodness forbid, you hit delete? Notice my screen doesn't have L1 anymore. And in fact, so what I'm going to do is I'm going to delete all of them. Okay? I'm going to delete all of my columns. Now, in that top left-hand corner, I need L1. I need to put it back. You will see right above the number 1 button, depending on your calculator, the color varies. We're going to press second 1, and L1 is back. Now I'm going to go to my next column. I'm going to go second 2 and hit enter. And now L2 is back. And if I had data in there, the data comes back with it. So we still need to press clear and hit enter. Okay, now, all right, hopefully we now have a blank screen, everything ready to fill in. Now, typically your calculator is going to default L1 is the input variable, so kind of like your x variable. L2 is the output, kind of like your y. So the dependent variable. So we're going to go ahead and type in the time for our L1s and the distances for our L2s. So I'm going to go ahead and just do that. So I'm going to type in 0, hit enter. I'm going to hit 1, hit enter, 2, 3, 4. And please let me know, yell out in class as I type in, because sometimes I make typos. So if you can tell me in real time so I catch my mistakes, that would be great. That was a joke. I will attempt to be funny. My kids will tell you they're dad jokes and they are horrible, but I do my best. Okay, so we're going to go ahead and type in all these numbers. Okay, so now you should have something that looks like this. I'm going to highly recommend to double check. Make sure you didn't miss a number. Make sure you didn't typo a number. I have 0, 1, 2, 3, 4, 4.3, 0, 3, 10, 21, 35, and 40. That looks good. All right, so our data is in our calculator. All right, so now what we're going to do is we're going to create a quadratic regression model. So what we're going to do, I'm going to go back to my main blinky screen. So I'm going to go second mode, which will put me back to quit. Okay, and that's working on those top row buttons. And I should be on a main blinky screen. If you have anything on here, I'd recommend hitting clear just to get it completely blank. And now we're going to go back to the stat button, right? We're going to go back into here. And now that our data's in, we're done in the edit screen. We need to go to calculate. So we're going to press the right arrow. And now in here, this is where we're going to choose our regression. And later on in the course, we're just going to tell you, find an exponential regression, find a logarithmic regression, find a whatever regression. So all the button pushing is the same up to this point. You put your data in the calculator the same way we just did. Now, for us, since we want a quadratic regression, we're going to go through this list and look for something that looks like it would be a quadratic regression. Oh, look at that, option number 5, quadratic. Now, but what if it wanted an exponential regression? Well, if you notice, you just keep arrowing down until you find the, oh, there we go. Option 0 is Exp regression. So if any problem ever asks for an exponential, follow all the same steps, just choose this, the option 0, or maybe a natural log regression, ln. So that's the one thing we're just going to remember, because later on in the course, there's just problems that are going to pop up in the homework. They're going to say make a regression, and you're going to have to remember to come back to this screen to do this. Okay, so for us, we're in quadratic regression. I'm going to hit enter. Now, notice the default in my calculator was xlist. Where did I put my x variables? Where did I put my independent variables? L1. Where did I put my y variables? L2, right? It's already defaulted. If yours has something else, you would type in the exact same way we just did by just pressing second number 1. It'll put the L1 in there, and the L2 in there. But if you have nothing else, then we don't have to worry about any of this. Just leave that all alone, and you hit calculate, and we hit enter, and there we go. We have our regression, okay? So, and then if you want to, you could draw a quick sketch of this model if you'd really like. Now, so now we have to make sure we read this, right? So what is this saying for our model, right? And for those of you with the old graphing calculator, we'll come back to you in a second. Give me 1 second here. So just follow along with what you're seeing on the screen. So you'll see, what are we getting out here? We're getting out y equals ax squared plus bx plus c. What does all that mean? Well, notice right below it, the a values are right there. It's 1.843054973 x squared plus, what's our b value? 1.413, whoops, 3991967 times x, because up above it says it's b times x, and then last but not least, it's just plus c following that model. Oh, but notice it's a minus sign, so we're just going to change that to minus 0.09830345. So you'll see that is our regression that we're going to be using. Okay, fantastic. Now we have a model, right? Now let's go ahead. For those of you, bear with me, for those of you who have the new operating system, you're good to go. But for those of you with the old operating system, when you hit your linreg, your screen, or sorry, quadreg, your screen just popped up with this. It maybe just had, excuse me, this on your little blinky screen, and you're like, oh my gosh, what do I do now? I didn't have that fancy chart. Well, as you saw, the system had it typed in for me, right? The system had it typed in. Whoops, let me go back. this is what was really being typed in. Quadrag L1 comma L2, right? So if you wanted to, after your quadrag, you would just, just go ahead here into the screen, and you would just type in second number 1, comma, second number 2, and you'd get the, whoop, no, I missed the second key, second number 2. There we are. And you'd hit enter, and you'll get the same thing that we got, okay? Now, this is going to be a lot of fun, but here's the issue. I want this. I'm going to want to use this equation for something. I would like the calculator to be able to type in values for me, right? So the problem here is these numbers are not fun. So why don't we do one extra little thing? So for those of you in the new operating system, we're just going to go ahead and hit stat. We're going to go right back to quadrag. We're going to go right in here. Now, do you see where it says store reg EQ, store regression equation? What we're going to have the calculator do is actually type this equation into our Y1 line for graphing. So that way we can plug numbers into it. We can substitute values into it. So how we do this is we are going to, from this screen, we're going to press the vars button, which is just down to the left of the down arrow. And what we're going to do is we want this in the Y variable screen. So I'm going to arrow over to Y vars. And so now notice it's either asking what kind of Y variable do we want, a function, a parametric equation, or a polar equation. Well, the good news is we don't know what any of those things are except for the function, so we'll go with that. And we'll leave it in the Y1 line. We'll just go ahead and have it typed right in Y1. And now when I hit calculate, you'll notice it's going to look, excuse me, oh, I think it may not have liked that I already had things in here. Let's go ahead and clear out all this stuff. I'll try that one more time. There we go. I think it didn't like that I had something typed in there. So if you have anything in there or you get that error, just clear out your Y1 and try again. And now what you'll notice, the kind of neat thing, is notice what it typed into my Y1. 1.8435. It's all typed in there. Now, for those of you with the old operating system, you're going to do the exact same thing you just did, except after your L1, comma L2, you're going to do comma, and I'll walk you through it one more time. So you're sitting here with the quadrag L1, comma L2, and then you just put another comma, which is located right above the 7, and we're going to go vars, arrow to the right for Y vars, enter for function, Y1, and it will do the same thing. It's going to take our function and type that in. Yep, it doesn't want to do it because I've got something in the Y1. I'm going to clear that out and go over here, clear it out. Let's go try this one more time. There we go. Okay, and now you're going to notice it's going to type in that equation into our Y1 line. So now we've got this typed in. We're ready to go. I've got it in my calculator in a way that I can graph it. I can sub in values looking at the table. There's lots of fun stuff I can do. All right, so let's keep going here. So part 1, we created a regression equation that's going to model this data. And I'll show you very quickly if I just quickly graph this data. Quit it. Stop. Let me turn on my plots just so you can see the fit. You don't need to worry about this. What I'm doing is turning on my plots. It's this top left-hand corner. I'm going to make sure it has a dark box around it. And then what I'm going to do here is go zoom, and I'm going to go zoom stat. So it will be based, there we go, option number 9. So it's based around the plots that we put in. And you can see there is our graph and there is our points. It looks pretty good. It's a pretty good fit. Okay, so now if you ever go to hit graph and it yells at you, what I'd highly recommend is for a later problem, turn off the plots. Go up here to the plot, hit enter, turn it off, and now you'll notice it's just going to graph the line, but not the points. Because a lot of times when those points get changed, it gives you lots of errors. So there we go, great. All right, ready to move? Let's keep moving. Let's do something with this function. Now, using your model from part 2, right? So using your model from part 2, find the average rate of change of the following time intervals. Okay, super interesting, super interesting. Notice these are not parentheses. These are not parentheses. So first visual clue, this is not an ordered pair. This is not an X and a Y value. No, no, no. This is an interval notation. It's starting at 1, ending at 2. These are both these are both X values or T values, whatever you want, time, whatever you want to call them. So therefore, to be able to create the average rate of change, ooh, there's that key word. That's just secret word for slope, y2 minus y1 over x2 minus x1. I need two ordered pairs. How am I going to get them? How do I get my ordered pairs? Okay, well, we are going to go to our function, right? We already have it typed in here. So now what I'm going to do is use my table in the top right-hand corner. I'm going to go second graph. And I like this mode. Some of you may already have numbers filling in, so let me show you how to change this. Why I like this mode is I can type in number 1 and get out my number, or I can type in the number 2 and get out my number. I can type in whatever I want to type in. So you'll notice in the next problem, I'm going to need 1.5. And then I'm going to need 1.1. So if I have it in the mode where I can't type it in, it's much more difficult to do. So what I'm going to do is notice above window, there is an option that says table set in blue writing. So I'm going to go second window. And now the key to this, you can put your start and your change in table, whatever you want. It doesn't matter because we're going to change this. If you have auto with the black box around it for the independent variable, we're going to go over to ask and hit enter. Now, when I go back to my table, I can type in whatever numbers I want. It's going to ask me to what I want. So how did I get to the table again? That was second graph. That put me right back to the table. So now for finding my average rates of change, right? I kind of have some ordered pairs. I know when I plug in 1, I get out 3.1587. Please note, these are very rounded numbers. This is not exact. And if I go up and actually put my little black box around this, I get a lot more decimal places of accuracy. So I can see this is 3.158743488061. And when I sub in 2, I get 10.1019003657. Yay, data. This is not pretty, but that's okay. How do we find our slope? Well, it would be y2, 10.1019003657, minus 3.158743488061 divided by, so that was y2 and y1, right? y2 and y1. Now I need to subtract x2, so that would be 2, minus x1, so that would be 1. Okay, this is not going to be fun. This is definitely not going to be fun, so I'm going to cheat. I'm going to show you guys a way to do this in the calculator that you may not have noticed was possible, but so might as well show you. So watch, check this out. What I'm going to do here is I'm going to go to my vars button, and I'm going to go to my y vars. Oh, I apologize. I am starting from my main blinky screen. So I've moved out of the graph. I've moved out of the table. I just went second, quit, went back to my main blinky screen. Now let's go vars over to y vars function y1 because that's where I typed in my function. Right, I typed in the y1 line. Now the neat thing is your calculator recognizes function notation. So this numerator came from what? Well, it came from me substituting in 2. So it's y1 evaluated at 2. And then I want it minus vars, y vars, function y1. I want y1 evaluated at 1. So now when I hit enter, I get that my numerator is 6.943156885 divided by, and the denominator, I know, the calculator, I could have it do it for me, but I think I got this one. 2 minus 1, that is 1. So therefore, the slope is that. Okay? So, that's kind of cool, right? But what does it mean? What did we just find? Let's put some units on this, right? What was my output? My output was describing distance measured in yards. Okay. So this numerator would have been 10.10 blah, 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 minus 3.15 blah, 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 yards per. Now the denominator was time measured in seconds. So this would be 2 seconds minus 1 second, which give me seconds. So therefore, my units would now be yards per second. So what does this mean? What does this mean? Well, I know in the time interval from 1 to 2 seconds, whatever this object was, it was traveling, right? And it was traveling at an average rate of change of 6.943156885 yards per second. Okay, now we kind of cheated. I just did this part right here for the first one, right? We just described the meaning. At the end of every problem, I always want you to ask yourself, what does it mean? It's not just a number. What does the number mean? Does it have a representation that's important? Okay, so from 1 to 2 seconds, on average, the speed our thing was going 6.94315 yards per second. All right, so now we're going to do this again. We're going to do this again for 1 to 1.5. Whoops, wrong window. There we go. So how can I do this? Well, you'll notice I don't need to really write out my points. I could just use the calculator. So I'm just gonna type in again. I'm gonna go vars, yvars, function y1, and I want to sub in 1.5. And then now I'm gonna minus vars, yvars function y1, and I'm gonna sub in 1. So now I know that the y of 1.5 minus the y of 1, that numerator just got spit out for me in the calculator. What did it just spit out? Whoops, what did it just spit out for me? It says my numerator is 3.010814699 divided by 1.5 minus 1. So I can divide by, now this is again math I can do in my head. What's 1.5 take away 1? Well, that's 0.5. So that will result in a slope. This was slope. That's going to result in a slope of 6.021629399. Units are still the same, yards per second. Right? So big idea. Hopefully this is coming together. Hopefully this makes sense. So we're going to just keep doing this. Now, of course, you could do this by hand. It would just be very painful, right? So now I'm going to show you even another trick. Now, in the calculator, do you notice above the enter key is in blue writing, it says the word entry. What I can actually do is press second enter, and it brings up the last thing I typed. And then if I do it again, second enter, brings up the thing I typed before that. Now that's super useful for what we're doing here because I'm always, do you notice, it's always starting at 1. So I just need to change that first number from 1.5. Now this is just going to become 1.1. So I'm going to arrow over. And I'm just going to go over here and say this is 1.1. I hit enter. And there we go. There's my numerator. So now my slope for this one is 0.528440741 divided by 1.1 minus 1. So again, I can do this math in my head. The denominator is 1.1 minus 1. So that subtracts to make 0.1, right? So we're going to make that 0.1. So in my calculator, I'm going to take my previous answer, divide by 0.1. There we are. So therefore, my slope is 5.28440741 yards per second. Now, some of you may also be sitting here thinking, you're like, wait a second, he's writing out all these decimals. Why isn't he rounding it? And the real short answer here is, in the class going forward, if it doesn't tell you to round, you don't round. Now, the one challenge to this is when we do regressions, we're going to get funky data. So we're going to tell you to round. So that's coming in just a minute. We're going to round. But unless the problem tells you, you can't round. So do not, and remember, the numbers coming out of our calculator are rounded answers. So this is that one moment where things are going to be a little strange and we're going to be dealing with kind of weird numbers. But then after I promise you after that, it's going to become real clear about what to use. All right, so I just did second enter, and now I'm going to go back over here and I'm going to say, okay, I want to type in 1.01. Well, notice above the delete in blue writing is the letters INS. That stands for insert. So I'm going to go second insert 0, and then that lets me insert that extra decimal place that I need. And so this is going to give me the slope of 0.511853246 divided by 1.01 minus 1. So that denominator would be 1.01 minus 1, which would be 0.01, with that numerator being that horrible, ugly number. So we're just going to go ahead and rewrite that as 0.01 divided by 0.01. And there we go. So we now have a slope of 5.118532462. And oh my gosh, we are done. Oh no, one more. One more. We can do it. We can do it. All right, so we're going to second enter. Second enter. We got this. We're going to go back over and say, I need to put another 0 in here. If I type, it's just going to type over it. So I'm going to go second, delete to put in the insert. I put in another 0. I hit enter. And there we go. My slope is now 0.0051011945 divided by 1.001 minus 1. And as we know, this will subtract to just result in 0.01. All right, so divided by 0.01. Ruh-roh. Something doesn't feel right about that. Oops, I typed in an extra... Nope, I didn't. I just didn't type in a 0 down here. Excuse me. So this shouldn't be that. This should be 1.001 minus 1. There we go. So notice when we subtract, that should give me 2 zeros. All right, so let's get back in there. Let's do this again. I'm going to go back here. Now you'll notice this numerator was right, but my denominator, I just typed it in wrong. Right? I had typed in, if you'll notice, only 1 0 instead of 2. So we're going to go ahead and put 2 zeros in there now. There we go. That number looks better. So that's going to give us a slope of 5.101944967. All right. Fantastic. That was a lot of work. Now notice all of these would be yards per second. Yards per second. So what is the meaning of the values, right? What are these? These are all giving us speeds, right? These are all different rates of change. These are all how fast was the thing going on average. So on average, from 1 to 2 seconds, we were going about, about 7 yards per second. But if we shorten that up, and we only go from 1 to 1.5, that number was about 6 yards per second, a little bit, 6.02. And then if we shorten that up even more, we go, okay, what was that? That was from 1 to 1.1 seconds. So notice this time interval is very, very short. The original time interval was 1 second long. It was starting at 1, ending at 2. Then the next one was at half a second long. Right, from 1 to 1.5. Now we're going from 1 to 1.1. This is 0.1 seconds. 0.1 seconds. That's not very long. That's a tenth of a second. On average, in that tenth of a second, we were going 5.28 yards per second. All right, cool. What is this? This is a hundredth of a second, right? A very short interval. How fast were we going? 5.118 yards per second. Does that mean we went 5.118 yards? No, it's just the speed we were going at that time, right? It's the average rate of change, yards per second. Okay, so then last but not least here, this last one was 0.001 seconds. That was a thousandth of a second. Over a thousandth of a second, our average was 5.10 yards per second. Notice, look at these numbers. When we went, so these don't get confused. I'm just going to change this one to purple. There we go. When we went from the purple to the blue, when we had a big time interval, our average rate of change was like close to 7. And then we went to the blue, we started shortening that up. We got down to 6 seconds. And then when we went from the blue to the orange, we went down to 5.28 seconds. We had kind of big jumps, right? The average rate of change was 6.9, but then we had a change of almost down to 6, and then we had a change of almost down to 5.2. But then as our time intervals started getting really, really small, how much we changed was getting really, really small. Do you guys agree? Do you guys agree? Okay, so what conclusion can we come to when comparing the values from above? Like going from A to B to C to D to E, looking at those values, what do we come up with? Well, let's think of it this way. Instead of seconds, let's just pretend these were for hours, right? For an hour. From 1 hour to 2 hours, how fast were you driving? We were driving on average 6.94 whatever yards per hour. That would be really slow, but whatever. So that would be a big time interval, right? From 1 to 2 hours, that's a big time interval. That's a lot of time to go by. But then the next one was 1 to 1.5. That's a half hour. I mean, that's still a pretty good time interval. But then 1 to 1.1. Wait a second. Now our time interval is getting really, really small. It's getting really, really quick. So do you see, by the time we get to the 0.001, that's like basically no time passing at all, right? From here to here. So let's go back to seconds now. Let's go to our thinking. Like, how long is 0.001? Sorry, yeah, 0.001 seconds. That's like instantaneous, right? That's like from your mom calls or your dad calls or somebody calls and says, how fast are you going? That's the amount of time it takes your brain to process, to look at the speedometer, to answer that question. So in the beginning question, you were talking about an actual average rate of change, right? We were talking about how fast were you going on average? Well, from 1 to 2, I was going 7, right? But if someone called you at 1 and said, how fast are you going right now? What would be your answer? It wouldn't be 7, right? It would be that really, really small time interval, the time interval it took for you to look down the speedometer and answer that question. It may have changed a tiny bit, but that's basically your answer. What is your answer? We were going 5.10, whatever, right? But what if I added in another? What if I kept doing that? Do you really think like that number is the end all be all of all the numbers? Or do you think that if I keep adding in more zeros, we might get even closer to a number, right? That there might be more change. Let's try this. Let's put in another 0 here. Let's go second insert 0. Ooh, okay. So now it's not 5.10, 1. It's 5.100. And then, of course, I have to divide this by the 0.00. Let's make sure we get the right number of zeros in there. 1. I missed the 1. I got the right number of zeros this time. There we go. There we go. So do you see? That one came out to be 5.100. What if, oh goodness, it's so hard to type on this computer screen. Let's just, bear with me. I'm going to get back up here, get one more 0 in there. There we go. What if I get one more 0 in here? What if I get to second insert? Right? The difference between 1.00001 and 1. Okay, now I'm going to divide by 1, try again, 0.12341. Do you notice something? It looks to me like even though this is not our exact answer, right? It doesn't look like we're approaching a certain value. It does look like no matter how many zeros I add in there, it looks to me like our slope is going to be 5.1-ish. Would you guys agree with that idea? Right? Now, looking up above from 6.9 to 6.02 to 5.28 to 5.11 to 5.10, can you look for a pattern and kind of make a conjecture to what you think the instantaneous speed would be? Like that at this moment, how fast were we going, right? Now, clearly, it's not going to be this number that we saw with the thousandth of a second, even though it's really, really close, right? But as we keep going, these numbers kept going 5.100 and then 5.10000, right? It kept adding on the zeros. It kept getting more and more, it kept changing, but it kept getting closer and closer to looking like it was going to get to 5.1. So could we make a guess, make a conjecture that the rate of change would become 5.1? That's the goal. Okay, looking at the numbers above, whenever we ask you about a instantaneous rate of change, right? What were you going at an instant? Is a thousandth of a second or a hundredth of a thousandth of a second that instant? No, there's still a gap, right? There's still a hundredth of a thousandth of a second going by. But can you use the pattern you see in the numbers, as you go along, Can you use the pattern to make a guess to what you think the slope at that moment would be? I would agree. I would think so. So what we're going to guess is the instantaneous speed was 5.1. So the average rate of change is what you saw up above. Okay, the instantaneous, if I could spell that word, it's not going to come out. The instantaneous, I don't think that's right, but whatever. The instantaneous rate of change is what you see from the pattern above. We see it by sliding the 2 points closer and closer in together. So do you notice we're starting at, the distance of how, if we were thinking about these, well, we'll get to this in a second. We're going to graph this in a second. So, but it's from the pattern above. So, and it's your guess. What did we guess? We guessed that it was a slope of 5.1. Still the same units, yards per second. Okay? All right, so using the model above, draw a line connecting the start times. Okay, so the model above, it's a parabola. Now notice, we using a sketch of the model above. So what I'm saying here is I don't care. When we say the word sketch, it's just supposed to be here to give us a visual idea. It doesn't have to be good. All right, we're not really going to worry about it. We're just going to get a sketch. Now, you'll say, all right, this is 1, and we'll call this 2. All right, so looking at the behavior of the lines, what can you say? Oh, sorry. Using a sketch of the model, draw a line connecting the start and end times describing each interval. Okay, so the first interval was from 1 to 2. So if I were to connect the dots, we knew that this slope was 6.9-ish, right? Okay, great. What was the next one? That was 1 to 1.5. So notice that line. Okay, great. So this slope we knew was 6.02-ish. Okay, fantastic. Notice what's happening here. The next one was 1.1. Hey, wait a second. That line's really close. The points are getting super close together, aren't they? And notice this slope was, what, 5.2-ish, 5.3-ish, 5.28-ish, right? These slopes are getting closer and closer together. The points are getting closer and closer together, and the slopes are getting less and less steep. We started with a very steep slope, right? This one was the steepest at 6.9. Then we went to one that was less steep at 6.02. Then we went to one that's even less steep at 5.28. What's happening? As I slide these points closer and closer together, do you notice it's almost as if I was going to draw a line connecting the two dots? That might look something like that. Okay, so let's clear all these out of here. Let's get a little vocabulary. Let's get a little geometry vocabulary in here. So you'll notice, do you remember from geometry, we had what's called a secant line. A secant line was a line that was going through a shape at 2 different points, right? So the green line is secant, the purple line is secant, the orange line was even secant, even though it's a really tiny little line because the points are so close together. But notice this black one and the green point, they are so close together. Like they are so right on top of each other that essentially I can't even draw a line. So if I just extend it out, this is looking more like a tangent line. What is a tangent line? That was when a line that touches a graph at 1 point. At only 1 point. Secant lines were lines that touches at 2 points. Now, the black line technically really isn't a tangent line because it is really going through 2 points, right? But one of the points was 1 and the other one was 1.0001 or something like that. It was so close that they're basically right on top of each other. You can't tell the difference. So when you connect the dots and you draw that line out, it looks like a tangent line, doesn't it? So, okay, so this is interesting because a tangent line is a line that touches only at 1 point. So if we were to find the slope of that tangent line, what did we say the slope was? That slope, when we said that the points were so close together we were going to make a guess. Oh yeah, we said that that was 5.1. Okay. So our slope is 5.1 yards per second. So interesting. So the tangent line, right now, we're gonna figure out the slope of the tangent line by sliding the 2 points so close together that they look like they're one of them, right? But how do we actually calculate the slope of the tangent line? Well, that's from what we did above. How do you calculate the slope of the tangent line? You start with 2 points that are far apart. You start with them at 1 to 2, and then you slide them closer and closer and closer and closer, and you look for your pattern, right? You have to look for what did the values do? What value were they approaching? It started at 7, then it got to 6.02, then it started at 5.28. So you have to kind of make a guess about what do you think is going to be next, right? Interesting. Okay, so the slope of the tangent line, we already said, is called the instantaneous rate of change. Slope of a tangent line, right, we said is the instantaneous rate of change. Because what does it mean to be instantaneous? Like right now, this instant, how fast are you going at this moment? Where the secant line, we said was from here to here, from 1 to 2. So this is what we called the average, if I could spell the word average rate of change. Okay, so secant lines are average rate of change. Tangent lines are instantaneous rates of change, or the slope of tangent lines are instantaneous rate of change, where the slope of secant lines is average rate of change. So how are you going to find the two different things? Well, secant lines, average rates of change, take place over long distances from 1 to 2, 1 to 1.5, 1 to 1.1. Those are long. What is an instantaneous rate of change? It's our guess. It's our projection about what it will be at that moment. For now, we'll have ways of calculating it later. All right, so any questions, please ask, right? Because this is the big conceptual idea. What is the big takeaways? Let's remember, what was our goal today? Do we know how to calculate average rates of change? Hopefully up to this point, you're like, yes, that's slope, right? How do I calculate instantaneous rates of change using 2 points that are very, very close together? Well, literally, I use 2 points that are very, very close together, and I make my guess, right? We're going to take 2 points that are far apart, take them and slide them closer and closer and closer. Go from 1 to 2, 1 to 1.5, 1 to 1.1, and so on and so forth. All right, and then, what's next on our list of things we need to be able to do? We know how to calculate average rate, instantaneous rates of change. Yes, that's our guess. Now we need to be able to write an average rate of change formula using H. All right, so good news. The theory is done. The vocabulary is done. That is the things, those are the buzzwords I need you to know. And if any problem asks for slope of a tangent line, what are they asking you to do? If they ask you for secant line, what are they asking you to do, right? Average rates of change, what are they asking you to do? We got all those things. All right, now, here comes some algebra. Okay. What if I ask you to find the average rate of change over the interval of 1 to 1 plus h of our model we created above? Okay, so for the model we created above, we are going to round our values to the nearest whole number for ease. Now, you're going to notice you're only going to do this in the homework if they tell you to do it. So the directions told me to do it, so that's what I'm going to do. For me to be able to copy this down, because this is not going to be easy for me to see. Hopefully for you it's easier because you have paper. For me it's hard to get it on the screen all at the same time. So what I'm going to do here is I am just going to very quickly go here. I'm going to go calculate quadratic regression. And I'm just going to pop down here just so I can see it on my screen. Calculate. Voila. Okay, so what are we going to call this model? I'm going to call it y. Let me change back to black. Y equals, okay. What did it want us to round to? Which decimal places? Be very mindful of that. Round your values to the nearest, here we go, nearest whole number. Okay, okay. So 1.8 divided to a whole number would be 2x squared. Plus, what is my b? That would be 1.4 would round down, so that'd just be 1x. So we're just going to call that x. And then minus, well, the c, the nearest whole number of 0.0, that would be 0, so I don't need anything, plus 0. Okay. All right. So now, how are we going to find the average rate of change over the interval of 1 to 1 plus h? Okay, well, we can't use our calculator to help us, but that's okay. That's okay, because what we're going to do is we're going to do it by hand. We're going to sub in the number 1. So if I sub in the number 1, right, to get my ordered pair, I'm going to plug in 1. What would I get? Well, this would be y equals 2 times 1 squared plus 1. So therefore, this would be what? 2 plus 1, so therefore y equals 3. Great. Okay, so I have my first ordered pair. I know when I sub in 1, I get out 3. What is my next ordered pair? Well, my next ordered pair, the next value on the interval is 1 plus h. That is the number I'm subbing in. So I'm going to say y equals 2 times 1 plus h squared plus 1 plus h. Fantastic. Okay. So now, for me to be able to work with this, for me to be able to find a average rate of change formula, I'm going to need my ordered pair written a little nicer than this. So I'm going to distribute through. I'm going to rewrite this as 2. I'll write it out once, just so we can kind of see, right? 1 plus h squared would be the same thing as 1 plus h times 1 plus h. So now I'm going to go ahead and distribute through the 1 and the h and the 1. So this is going to give us 2 times 1 times 1 is 1. 1 times h is h times 1 is h times h is h squared, plus 1 plus h. I don't need those parentheses. They're not doing anything because of the plus sign. No distribution or anything to worry about. So now I'm going to distribute my 2 through, which will result in y equals 2. H and h, right? These two h's would make 2h. So 2h plus, or times 2 would make 4h, plus 2h squared, plus 1 plus h. And last but not least, let's combine our like terms. So this is going to give me y equals 2h squared. Let's see, that's that one. I still have the h's, so that's going to be plus 5h. That's this and this, plus 3. Okay, great. So now this is going to seem a little funny, but my ordered pair is 1 plus h. When I sub in 1 plus h, I get out 2h squared plus 5h plus 3. Okay, all right. That's what it is. That's what it is. Now, how do I find the slope? This is no different. It is literally what we've been doing, right? It is the slope equals y2 minus y1 over x2 minus x1. Okay, so I have my ordered pair, my first ordered pair, which I'll use up here. I'll call this my x2 and my y2. So if I'm going to sub those in, I will have my slope is equal to y2, which is 2h squared plus 5h plus 3, minus, what is my other y value for my other point? Well, my other point was much more simple. It was 1, 3, so the y value was 3, over. Now for the other one, the x2 would be 1 plus h minus, right, then if over here for my x1, whoops, that would be y1. For my x1, my value was just 1. There we are. There we are. Okay, so therefore, now that's my slope. It's kind of ugly. It has h's in it. I don't care because they want my slope with h's. Fine. So now we combine our like terms. No dividing numerator denominator, right? We have plus signs. We can't divide yet. To be able to divide, we have to factor. So I'm just going to work in that numerator and say, what can I simplify? Like terms, 3 minus 3. That's pretty awesome. 1 Change colors. -1 plus 1. That's pretty awesome. All right, so what am I left with? Numerator, 2h squared plus 5h divided by h. Now I have the opportunity to factor, because in my numerator, I have an h in each term. So I'm going to factor out an h. Leave me with 2h plus 5, right? Common multiples are greatest common factor. There we go. So they each have an h. I'm going to take that out. And now in my denominator, I still have my h. And now I'm able to divide because I was able to factor. I have h times everything else. And in my denominator, I have h times, well, I mean, itself. So these are able to divide to 1, leaving me with the slope is equal to 2h plus 5. Cool. Okay. All right. So we were able to come up with an equation. We now know the slope is 2h plus 5. So what would it mean? What would it mean? So for part B here, if I know the slope is equal to 2h plus 5, what would it mean if h was 1? If h equaled 1? Well, go back to the original points. We were going from the point 1, 3, and then the other point was 1 plus h to whatever that horribleness was. What was that horribleness? 2h squared plus 5h plus 3. So what would it mean if I just let h equal 1? Well, then I would sub it in. And that would give me what? My second ordered pair would be, well, 1 plus 1, so that would be 2. And then if I sub in 1, let's see, this would be what? It would be 2 plus 5 plus 3, so 5, 6, 7, 10. So do you see we now have two ordered pairs? My first ordered pair would be going from 1 to 3. My second ordered pair would be going from 2 to 10. So if I were to ask you to calculate the slope, between 1 to 3 and 2 to 10, well, you'd be like, no problem, I got it. It's right, 10 take away 3 over 2 minus 1. So therefore my slope is 7 over 1, or the slope is 7. Cool. What if I just plugged 1 in over here? Slope equals 2 times 1 plus 5. So therefore my slope is 7. Really cool. Okay, so what's the idea? What did we just create with this equation? The slope equals 2h plus 5. I can now just plug in h values. So the idea here, like the whole purpose of this, if we kind of ignore the y values for a second, because we now have this really cool equation that does it for us. Right? What are we saying here? I want to go from an interval. If I want to go from an interval of 1 to 2, 1 to 2, how would I calculate that? Well, that would be 1 to 1 plus h, right? So what would my h need to be? Well, that would have to be 1. What if I wanted to do an interval of 1 to 1.5? Well, then what would my h need to be? Well, if my formula is 1 plus h, well, then my h would have to be 0.5. And then what if I wanted to do from 1 to 1.0 or 1 to 1.1? Well, what would my h be? My h would be 0.1, right? So the h represents the length of your interval, how long it lasts. H is 0.1 seconds or 0.5 seconds, or h is 1 second, right? The h is how long the interval, starting at 1, ending at what? And it's only starting at 1 and ending at what? Because we literally did, when we created our point, we did it as 1 plus h, right? Now, a lot of problems will do something like this, maybe 2, 2 plus h. And so notice these first numbers always match, because we're saying when I start at 2, what do I get? When I go to 2 plus some number, right? So that interval is going to be increasing. It's 2 plus another amount. So if h equaled 0.5, then our interval would be going from 2 to 2.5. So when we create these problems, we always pick h, so this number that's adding to the h to be the same. So 2 and 2 plus h, or 1 and 1 plus h. Okay, so good news, you don't have to worry about that. The problems are going to be built that way. So your job is going to be to figure out what those formulas are. All right, so let's do another one, right? So here you go. Here's another one, 2 to 2 plus h. How do we do this? Well, we start off by subbing in 2, right? We need that first order pair for finding our slope. So we're going to do f of 2, and we're going to say that is 2 times 2 squared plus 5 times 2 minus 4. So this is f of 2 equals 2 times 4 plus 10 minus 4. So therefore f of 2 equals 8 plus 10 minus 4. So therefore f of 2 equals, let's see, 8 take away 4, that's 4. So that'd be 14. All right, so we have our first ordered pair, 2, 14. So we're going to use that for writing our slope equation. Now we need our other one. We need our other point we're going to use, which is 2 plus h. So I have to do f of 2 plus h, which means everywhere I have an x, I'm going to replace it with 2 plus h. So it's going to be 2 times 2 plus h squared plus 5 times 2 plus h minus 4. So notice we're just subbing that back in to the original equation. Everywhere I had an x, I'm replacing it with 2 plus h. Now, to make our lives easier for the solving for our function, we're going to distribute. So remember, this is 2 times 2 plus h times 2 plus h. This 5 we can distribute, so this is going to be 10 plus 5h, and then last but not least, minus 4. Okay, now we're going to distribute all this through. Hopefully you remember from algebra your patterns for how these things distribute. This is going to end up being 2 times 2 is 4, 2h, and 2h is going to make 4h, and then h times h is h squared. If you don't remember it, just FOIL it through or distribute it through. You'll get it. And actually, I'll combine this 10 and this 4. We're going to put those together to make 6. Okay, moving right along. Now I'm going to distribute my 2 through. So this is f of 2 plus h equals 8 plus 8h plus 2h squared plus 6 plus 5h. All right. And now, and now when we combine our like terms, get these things in a nice little order. Let's see, this is going to be 2h squared. 8h and 5h makes 13h. So those are taken care of. The h squared is taken care of. So now I just have the constants, which is 8 plus 6, which would be 14. All right, there we go. There's our equation. So now comes the fun part. Now comes the slope. Slope is equal to y2, right? Remember, this is our y value. This is what we get out when we plug in 2 plus h. So therefore, it's y2, 2h squared plus 13h plus 14 minus y1. That came from here. This was our y1. So that's going to be 14 over x2, 2 plus h minus x1. That's from our ordered pair being 2. And beautiful things are happening again. Notice 14 subtracts with 14, and in the denominator, 2 subtracts with 2, leaving me with a slope that is 2h squared plus 13h divided by h. Hey! In that numerator, once again, we can't divide the h's until we factor. So in that numerator, take out your greatest common factor, which would be h, leaving behind 2h plus 13. In the denominator, there's nothing to factor. So now the h's divide, leaving me with a formula for slope equals 2h plus 13. That's amazing! We have a slope formula. So now when we want to sub in values to get the rates of change, the rate of change from here to here, from 2 to something, so the rate of change from 2 to 2.5, if I want that slope, I don't have to do any work anymore. All I have to do is say, what is my h? What is the change? Well, h was 0.5. So if I want the slope, I'll sub in 0.5, which will give me what? The slope would be 2 times 0.5 plus 13. So therefore the slope is equal to 1 plus 13. So therefore my slope is 14. So I know going from 2 to 2.5, the average rate of change is 14. That is so cool. So cool. So do you notice we've created like a function that tells us the average rates of change, and then if we wanted to, we could just pop that right into our calculator and let it spit out answers for us real fast. So what I could do here, I'm going to go into my y1 line, I'm going to hit clear, I'm going to type in, this would be 2, I can't use h, so I'll do x plus 13, right? And now, if I go to my table, I'm going to go back to my table. And now remember, my x's are not really x's. These are really my h's, right? It's my distance apart. So if I wanted them 1 apart, right, what would that represent? If I do h equals 1, what does that represent? That represents going from 2 to 3. Then if I wanted h equaling 0.5, that would be going from 2 to 2.5, right? Well, I'm just going to type in 0.5. Then what if I wanted to do h equaling 0.1? Well, I just type in 0.1. Whoops. And so now, do you see we can build a table to compare, to look for that instantaneous rate of change really fast. And so what we're doing is sliding these points closer and closer together. What we're saying is, what is 2 to 2.000000, right? We could do 0.001, right? What is that instantaneous rate of change approaching? Do we see a pattern forming that we are convinced we know what value it's going to approach? They started at 15 to 14, then 14 to 13.2, then 13.2 to 0.2, then 0.2 to 0.02, then 0.02 to 0.002. So notice it is rounding, right? It looks like it's 13, but it's not. So I'm pretty much convinced. I'm going to say that the slope of the instantaneous rate of change would be 13, right? So we could do that same thing back with this problem to help us, right? But I think at this point, hopefully we're getting it. So we've got one more problem here to do for practice. Now, this one's going to be the most challenging algebraically. The last two were simply, when I say simply, simple is a relative word. Simple is not easy for sure, but they were polynomials, right? We were subbing into a polynomial. This thing's not a polynomial. So notice we're going to go 1 to 1 plus h. All right, so here we go. We start off by saying I'm just going to plug in 1, sub in 1, see what I get. All right, so this would be 1 over 1 plus 8 plus, minus 1 over 1 over 1 plus 8. So g of 1 is equal to 1 over 9 minus 1 over 9. So we can simplify that numerator, saying 1/9 minus 1, well, common denominators, that would be 9/9 over 9. And then, so g of 1 would be, negative 8/9 divided by 9. If you understand what I just did, I said this symbol is the same thing as division. So this way I can more simply say this denominator being 9 is the same thing as 9 over 1. And so now how do we simplify fractions? We flip and multiply, right? If we divide fractions, flip and multiply. So this would be that. It'd be negative 8/9 times 1/9. So last but not least, negative 8 over 81. Got my number. Woo! All right. Now some of you might be like afraid. You're like, wait a second. Do we really have to do this with the 1 plus h? Why, yes, we do. Here we go. All right, so g of 1 plus... Let's try that again. 1 plus h. There we are. That's equal to 1 over 1 plus h plus 8 minus 1 over 1 plus h all over 1 plus h plus 8. All right. All right. All right. So let's combine, get this to look a little cleaner. That this first fraction in the numerator would be 1 over 9 plus h minus 1 over 1 plus h over, we'll make that another 9 plus h. All right, now what? How do we work with fractions? Well, remember in this last problem, there's lots of techniques. Okay, there are lots of techniques. So if this is not what you did in algebra and you've got another way of doing it, as long as it works, I'm happy, okay? You don't have to do it my way. But what I was going to point out is we did this problem by getting common denominators, didn't we? When we did 1/9 minus 1, we said, look, I need common denominators so I can subtract them. Okay, so common denominators, here we go. This denominator on the left-hand side is 9 plus h, so on the right-hand side, I need to multiply by 9 plus h. My pen's a little thick. Let me make this a little thinner so it looks a little cleaner. 9 plus h. There we go. Now on the right-hand side, it already has a 9 plus h. but it doesn't have a 1 plus h, so I'm going to give it a 1 plus h. I'm going to go ahead, scoot my equal sign over a little bit. There we go. So I'm going to give it a 1 plus h, but whatever I do to my denominators, I can't just do 1 plus h and 9 plus h in the denominators. I have to balance it. I have to do that same thing in the numerator, right? Because now I just really multiplied by 1. Right? And so 9 plus h divided by 9 plus h is 1. 1 plus h divided by 1 plus h is 1. So working forward now, I can look at this as g of 1 plus h equals 1 plus h over 1 plus h times 9 plus h minus 9 plus h over 1 plus h times 9 plus h. And the kind of cool thing is, all over 9 plus h. Now please notice, every line is mathematically equivalent. Pieces are not coming and going. Every line has that 9 plus h in the very bottom dividing. Like, it's got to be equivalent. No random numbers just appearing on the page. Okay, now notice, numerator, we've got common denominators. So we are going to rewrite this. I'm going to slowly make these pens all the smaller size. Okay, so we're going to rewrite this as 1 plus h, or sorry, g of 1 plus h equals. Now here, it's 1 plus h. Now notice it's minus 9 plus h all over 1 plus h times 9 plus h, right? Because the whole idea, that looks kind of like a g. I don't know, that 9's just not working with me. The whole idea here of getting common denominators is the numerators go together, right? The numerators, I'm just rewriting this off to the side, 1 plus h. There we go. Right? The numerators subtract, right? When we got our common denominators here, we said, look, my 1 minus 9 makes negative 8. What happened with my denominator, the 9 ninths, the 9 and the 9? It just stayed 9, right? That just stayed the same. Okay, so same idea here. Same idea here. Be careful because it's the numerator minus the other numerator, 9 plus h. So notice that minus sign is going to need to distribute. That's one of the most common mistakes is we forget to do that. Okay. So let's distribute this, and then we'll take a pause and we'll take a look at what we're looking at. So this is, let me get the smaller pen. There we go. So therefore this is g of 1 plus h equals 1 plus h minus 9 minus h over 1 plus h times 9 plus h all over 9 plus h. All right, stopping and pausing, just let's clean up that numerator just a smidge because this is kind of exciting because you notice we have an h minus h. That's nice. That's nice. And then in the numerator I also have, because that makes 0, right? And then in the numerator I also have 1 minus 9, so that would make negative 8. Okay, okay. So it's g of 1 plus h equals negative 8 divided by 1 plus h times 9 plus h, all divided by 9 plus h. That simplified out really nicely. Now, the last question is there any more simplification? Well, remember in the last problem, I said, well, wait a second. This fraction line, I'm going to write that as division. And this 9 that's in the denominator, I just write it as 9 over 1, right? So I can look at it as a fraction and a fraction. So we're going to do that similar thing. So notice this 9 plus 1, 9 plus h, we're going to call this 9 plus h over 1. Here we'll call this as 9 plus h over 1. And this big middle division line, we're going to rewrite that. We're going to rewrite that as g of 1 plus h equals negative 8 over 1 plus h times 9 plus h divided by 9 plus h over 1. So notice there's my 9. Ooh, I don't like that color. That's hard to see. Let's go with this one. 9 plus h over 1. That just went right there, right? Divided by my divided by symbol. All right. Now, how do we divide fractions? How do we divide fractions? That was supposed to be a black line. There we go. G of 1 plus h is equal to, the first fraction stays the same. So that's 1 plus h times 9 plus h. But the second one we flip and multiply, so we change it to times 1 over 9 plus h. Great. All right, now we're almost done. So g of 1 plus h equals negative 8, because negative 8 times 1 is negative 8, over Oh gosh, so what's going to happen here? This is 1 plus h times 9 plus h squared. Nothing to simplify, nothing to factor. That's all right. That's our formula. So how did I end up writing all these g of 1 plus h's, guys? Someone should have told me here at the very beginning. This isn't g of 1 plus h. What are we doing? I can't believe you guys didn't tell me. Slope, right? This was our slope formula. Slope. 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 Let's do it one more time. Slope. And if you weren't sick of it yet, we'll do, hey, that was supposed to be slope. And that is the slope. And what are we getting here? Slope again, which results in slope. So what did we just create? Our slope formula, right, with h. So therefore, I can sub in any number I want. I can sub in, for example, I can sub in h equaling 1, and I just have to remember, what did I just figure out? Well, if we started with our function,